Hello, welcome back. This is Fundamentals of Micro and Nanofabrication. I am Swayam from IIT Bangalore, and this would be the third lecture in the continuing series of CVD, where we are looking at the looking at the module of additive processing, and we are looking into the details of how chemical vapor deposition allows us to grow high quality epitaxial films. In the previous lectures, we have looked at some basic definitions of such as conformality, step coverage, etc. We then went into a little bit of detail in the mechanism of CVD. Specifically, we understood the role that reactor design plays in the growth mechanism of a CVD. It allowed us to discuss details such as what is a hot walled CVD, a cold walled CVD, what is atmospheric pressure CVD, what is low pressure CVD, and what are the different advantages and disadvantages of each of these techniques. In today's lecture, we will get into more nitty-gritty detail of the actual thermodynamics of the growth. Specifically, we will look at surface reactions, we will understand what type of reactions happen and how do we use those reactions to grow CVD. We will talk about nucleation, a very important aspect, though I would agree a little complicated, and we would like to understand how grains form, we would like to understand how films grow, and what decides whether you get large grains or small grains, what decides whether you are getting a 3D growth or a 2D growth. So, let us get started. So, this is where we left off in the previous lecture. We had just finished the module on gas flow, right. So, we had discussed everything from the flow of the gas to how diffusion through the gas allows you to get your precursors to the surface of the wafer where the reaction can occur. Next, we need to now talk about adsorption, because finally as the precursor makes its way to the wafer, it must get adsorbed on the surface. Very simply speaking, this process is the solid solubility of the material. You had seen this before when we were looking at the oxide growth, and for very similar reasons and very similar processes, every precursor would have certain amount of solubility on the surface, and depending upon what solid solubility it has, would decide what is the maximum concentration of the precursor on the surface, and the concentration on the precursor on the surface will then decide the growth. There is not much more to this. This process is fairly simple in most common CVD reactions. Of course, it can get complicated. All you have to do is pick up a handbook and figure out what is the solubility and equilibrium vapor pressure, and then take it from there. So, that was short. Let us get to the next module, which is the more which is a little larger one, and as I said, can be a little complicated. So, once the material, the precursor has adsorbed on the surface, then it must suffer the chemical reaction that would eventually form the film that you want to deposit. So, let us talk about chemical reactions, and once the material has formed, that is just a molecule of the material then has to adjust its way on the surface so as to form a crystal. Given that this is that we are depositing solids, this diffusion or this reorganization of the molecule on the surface can be fairly non-trivial, and we will look at some of those details, which is generally understood under the concepts of nucleation, right. So, first, chemical reactions. So, the idea of the chemical reaction is fairly simple. Whatever has adsorbed on the surface must react. Now, there are different types of reactions that can occur, and the details often depend upon what chemistry you are trying to do. Common CVD reactions tend to be pyrolysis or reduction. That is mostly because most semiconductors are not oxides, most semiconductors are reduced elements. So, if you want to deposit silicon, you often start with, say, silane, and you just heat it up at high temperature such that it would decompose into silicon and hydrogen. So, this is what is happening, for example, here. Let me grab my pointer real quick. Yeah, so this is what is happening here. So, silane is decomposing into silicon and hydrogen. Now, this silicon is solid, but at this point it is molecular solid, right. So, there is one atom of silicon. Now, it must rearrange itself on the surface if we were to do epitaxy, but to that we will come later. In general, the more unstable a precursor, the lower the deposition temperature, lower the temperature at which it would pyrolyze or break down. So, for example, nickel carbonyl break down at only 180 degrees C. For compound semiconductors, stoichiometry can become a little challenging. Here both silicon and nickel are elemental semiconductors, so there is no concept of really stoichiometry, but if you were to say deposit an oxide or you are trying to deposit a nitride, then you might need two components. So, that's when there are two components, stoichiometry or maintaining stoichiometry can sometimes become challenging. Pyrolysis, if you can find a precursor that can actually pyrolyze directly into a material without you needing to mix two components, is a huge advantage. So, a single component reaction means you do not have to worry about stoichiometry, and that is always good. Often pyrolysis is used for elements such as silicon, aluminum, titanium, lead, molybdenum, etc. And also in some cases for oxides, for example, you can get pyrolysis based precursors for titanium dioxide, zirconium oxide, niobium oxide. Those of you who are familiar may read up about alkoxides. So, the general class of alkoxides can pyrolyze to oxides. The second very popular class of reaction is reduction. As the name suggests, you just use hydrogen to reduce certain materials. So, and a good example would be you start with tetrachlorosilane, and which is a gas, and you react it with hydrogen at higher temperatures to form silicon and HCl gas. HCl gas floats away, silicon precipitates out, and you form your film. You can do something similar to deposit tungsten. If you start with tungsten fluoride, react with hydrogen, form HF gas and form tungsten. The disadvantage of, or rather something to take care about this technique is often these tend to be halides, which means that the byproduct that is formed is a halide acid, HCl or HF. Halide acids are very aggressive, they are very corrosive, and are also hazardous gases. So, you have to be a little careful in designing a reactor that does this. Often this is a two component reaction. So, you can imagine here you are flowing tetrachlorosilane and hydrogen together. So, if you are to get stoichiometric or pure silicon, you would want this tetrachlorosilane and hydrogen to be in some ratio. In this case, it turns out it is not too complicated, but in more complicated cases of a nitride or growth of an oxide, this can be an issue. So, reduction based mechanisms from a stoichiometry perspective can sometimes be challenging, it depends on details. This technique is often used to deposit silicon, tungsten, aluminum, etc. The next two classes that are less common but still must be discussed is oxidation and the general class of others. Oxygen often tends to produce oxides, I mean obvious. So, and most oxides are not semiconductors, or at least not popular semiconductors. So, oxidation as a technique to do in CVD is often less used. Still, if you were to want to deposit silicon dioxide, for example, you can take silane, put in oxygen and form silicon dioxide. Again, this is a two component reaction. So, for stoichiometric sake, you may need to do some fine tuning in how much silane and oxygen you flow through. The other things that, so a whole bunch of oxides of silicon, tungsten, aluminum and titanium can actually be deposited like this. The other the general class of others includes, supposing you want to form nitrides, you can react BF3 with ammonia to form boron nitride, or if you want to form carbides, you can react tetrachlorosilane with methane to form silicon carbide. There is also a possibility of using disproportionation, where the same molecule both oxidizes and reduces at the same time. For example, germanium iodide can disproportionate into germanium solid, which is the semiconductor you want to deposit, and germanium iodide, which is a gas which floats away, though such reactions tend to be rare. The final point I would like to make is that what reaction you are using is fundamentally decided by the precursor you are trying to use, and designing a precursor is a research problem in its own right. There are a lot of people who design novel precursors and see how useful those precursors are for CVD applications. The goal in most cases is to design a precursor that is safe, that is volatile, that decomposes or forms the material cleanly, that does not have side reactions that can occur which will lead to impurities, and the byproducts of which are safe, etc. So, those are the typical goals of a good precursor design and a good chemistry. So, here is an example of something from my own lab. So, we are using copper acetonate, which with oxygen and heat decomposes into copper. Now, here is an extrinsic example, because this is a two component reaction in which you can form either copper or Cu2O, which is the +1 oxidation state of copper, or the +2 oxidation state of copper, or something in between. So, And it really depends upon a lot of details. For example, how much oxygen you are flowing. So if you don't flow any oxygen, we tend to get copper. So here is an example where on silicon dioxide, we see these peaks which correspond to copper. If you increase the oxygen concentration, this reaction starts occurring and you start forming Cu2O. So for certain concentration of oxygen, we start seeing a mixture of Cu2O and Cu. So you see these peaks which corresponds to Cu, and this one peak which corresponds to Cu2O. And if we increase the oxygen even further, then we start forming the fully oxidized form CuO. So this is what the XRD looks like, where all these peaks correspond to CuO. But it's even more complicated than that. If you now look at this, that we don't just have silicon dioxide substrate, we actually have ITO substrate, FTO substrate, silicon and glass, and there is also a huge dependence on substrate, right? This is a very interesting observation. The reasons for this, however, will not be clear in this lecture. You might need to see the following lectures to completely appreciate it. But it does highlight the fact that CVD is a very versatile technique. You can get very different types of materials, and there are a lot of levers you can tune, there are a lot of details you can look at. Comprehensive CVD comprehensive understanding of CVD would require a lot of experience and essentially a course on its own. This course will not try to do that. What we will try to do is just highlight the basic concepts. So at least you are empowered to go read papers on chemical vapor deposition, and hopefully that will serve as a foundation from which you can learn further. Okay. So I will not try to completely teach you CVD, but get you a sense of how it is done. All right. So let's now talk about how do we predict this. So I just gave you an example where there is a precursor, it reacts with oxygen and it can form any metal. It can either form a metal or an oxide or a different oxidation state of the oxide. So is there a better way to predict what would occur than just doing the experiment empirically and trying to figure out what is happening? So it turns out no, chemical engineers have figured out how to calculate these things or simulate these things, and here is an example of how you would do that. So for any general chemical reaction, say A molecules of A reacting with small b molecules of B to form C molecules of C and D molecules of D. This reaction would have a Gibbs free energy change. That's why this reaction is happening, right? And this Gibbs free energy change must be negative, and it's given by this relation. Now at equilibrium, the Gibbs free energy change is 0, which is what defines what this delta G naught is. Now once you know that delta G naught, and this is often known because these tables have been constructed where, and their softwares exist, where given a certain reaction, they can tell you what is the delta G naught of this reaction. So once you know the delta G naught of the reaction and you know the temperature at which you are doing the reaction, then the only thing you need to know is the activity of the various components involved in the reaction. The activity in case of gas phase reaction is nothing but the partial pressure divided by the total pressure. So the percentage of pressure, like what is the concentration. So this is very easy to calculate because as we have discussed in the previous lectures, in CVD you typically flow material, there is a total pressure, there is component pressure, and by Dalton's law of partial pressures you can calculate what those partial pressures are if you know the flow rates, right. So that we know. So if we can figure out this AI, then all we have to do is plug this AI back into this reaction, calculate the delta G, and if the delta G is negative, then that reaction must occur. So the takeaway message from this slide is the following. Given a certain chemical reaction that must happen, you can calculate its delta G given the partial pressure of the components. The delta G is a function of temperature, right. So delta G here is a function of temperature. So if in order to make a certain material, you need to figure out under what conditions of temperature and under what conditions of partial pressure is your delta G negative, and for those range of temperature and pressures you will actually get this reaction to occur. So you can figure out what is your window of deposition, right. So this is how you do this. So here is an example again of something that happens in my lab. So this is we use a software called HSE chemistry, and using this HSE chemistry software we were trying to calculate under what conditions of temperature and under what conditions of pressure would we form copper oxide. So it turns out that at low temperature we form CuO, at high temperatures we form Cu2O, and in the middle we form a mixture of the two, right. And this becomes a very handy guide to guide your experimentation. Sometimes your experimentations can be a little off towards left or right, but this does provide very good idea of which direction you should tweak your parameters in order to get the material you need. One final clarification, everything we have talked out till now is all about thermodynamics, right. So, this is what would occur given infinite amount of time, but when we are doing CVD in a realistic reactor, we do not have infinite time, which is another way of saying we should also be careful about the kinetics. The kinetics and the thermodynamics can sometimes give you different results. So, with that I will just leave it at that, and we will come to some kinetic factors later in the lectures. So, let us now talk about nucleation and growth, right. So, what we have done, just to summarize, we started with the gas phase, we adsorbed on the surface, we did a surface reaction, and now we have this, say, one atom or one molecule of the material we want to deposit. Now, this material must reorganize on the surface. So, how does it reorganize? So, that is the discussion of nucleation and growth. So, first let us generally understand nucleation. Now, very frankly, we have visited nucleation before when we are doing crystal growth. The concepts we are going to discuss right now are exactly relevant even for crystal growth. So, I will be using the same terminology of supersaturation. If you have forgotten or you would like to refresh your memory, I would urge you to go back and look at those lectures of crystal growth. But the basic idea was that at any given temperature and pressure, any material will have a certain equilibrium, which is that it will exist in a for example, a solid will have a certain vapor pressure, or a liquid will have a certain vapor pressure. Now, if you were to keep that system at equilibrium, then there would be a kinetic equilibrium where there would be adsorption of that material on the surface, there would be desorption of the material on the surface, these two would be equal. So, the net concentration of the film or the net thickness of the film would not change. However, if you were to make this system go into non-equilibrium and specifically supersaturation, then adsorption would be higher than desorption, and you would then have a driving force for transporting the material onto the surface and reorganizing. Now, the way this happens in CVD is that you form this molecular atom by this chemical reaction, and these small atoms of chemical reactions, for the purposes of this part, can now be thought of as small nuclei, right, a small nucleus or a nucleate that is now trying to move around on the surface, all the time trying to reduce its delta G, right. So, the delta G is negative if the system is under supersaturation, which means that the chemical reaction is trying to go towards the right. Okay. So, you have put the pressures in this pressures in this reaction in such a manner that this delta G is negative. So, this reaction is moving from the left hand side to right hand side, and as this reaction is moving from the left hand side to right hand side, you are depositing more and more of the material on top of the wafer. So, now the system is supersaturated, the delta G is negative. Now, but that is, as I said, all thermodynamics. Given infinite time, the material will nucleate out, or the material will start forming a crystal. There is a certain kinetics to it. So, just remember that, okay. That in finite time does it happen or not really depends on nucleation rate. Now, the first concept of nucleation that we must discuss is homogeneous nucleation. Now, this is the nucleation that does not happen on the surface, but rather happens in gas phase. So, this is not what we typically do in CVD, but just bear with me for 1-2 slides, you will see that this is relevant. Now, imagine that you have a container, right, and in that container you have pushed in a certain precursor, and you have made sure that the pressure of the precursor inside the system is higher than its equilibrium, right. So, you have made sure that the system is under supersaturation. So, now the system is ripe for chemical reaction. So, now the left hand side of the chemical reaction will try to go to the right hand side, right. Now, the Gibbs free energy associated with this transition is given by this, which is simply the logarithmic of the difference in pressure. So, when the P surface is equal to P equilibrium, then of course the system is equilibrium, delta G is 0, but as the partial pressure on the surface increases, then this whole equation becomes more and more negative. So, there is more and more driving force towards nucleation. Now, when material ultimately does nucleate, then it's reasonable to assume that it will form a sphere, because this is a gas phase reaction. So, it should not be biased in any particular direction. So, you assume that it will form a sphere, but when something forms a sphere, it gains something and it loses something. So, what is it gaining? Well, it is gaining this energy, right? It is gaining this gives free energy, and since the volume of a certain sphere goes as r cube, you assume that if the radius of this nuclei is r, then it would gain energy as a function of r cube. Bigger the radius, more the energy that you have gained. However, you do lose something, and what you lose is you lose surface energy, because now you started with a system that was just gas phase, that had no surface, but now you have formed a bubble, you have formed a small nuclei, and that nuclei now has a surface, so must have some surface energy. So, you must pay the penalty of this surface energy. Now, so surface area of a sphere goes as pi r square, the surface energy loss scales with r square, larger the radius, more the energy. Overall, there is a net change in free energy due to nucleation, which is given by this, right. So, there is a surface component that scales with the surface area of the nucleus, and a volume component that scales with volume of the nucleus. Now, if you want to plot these two things together, as r increases, you would see that there is a relation. Now, just to highlight this delta term is negative, right. So, this is positive, this is negative. So, as your r becomes larger and larger, your G surface increases, but so does your delta G volume, and the subtraction of these two is the net red curve that you would get, which is your delta G homogeneous nucleation. Because of the way the polynomials work, the delta G surface goes up slower than delta G volume, because remember, this is an r cube and this is an r square. So, ultimately the delta G volume will win out. So, for very large r's, your delta G would be negative. The delta G homogeneous, the net delta G would be negative. However, for small r's, the penalty of making a surface is higher than the gain of saving some volume gives free energy. So, for small r's, you actually have a penalty of formation. So, your delta G is positive. What this means is that nuclei do not want to form when they are small, but nuclei do want to form when they are large. But since we are doing a chemical reaction, at some point this must be initiated by just one molecule, right. Like this has to be initiated at some point. You can directly make a very large nuclei. So, then how does that work? So, what that works is that whenever you start the nucleation process, there is a certain barrier. You do not immediately form a nuclei. What must happen is that the small nuclei keep forming, desorbing, forming, desorbing. There is this dynamic equilibrium, but that equilibrium is slightly biased towards formation, right. There is more adsorption than there is desorption, and just by statistics or just by chance, some of the nuclei grow a little larger by coalescing with smaller nuclei. So, the smaller nuclei keep shrinking, the larger nuclei keep growing, and there is this critical nuclei r star, which is the boundary of this difference. If your nuclei is larger than r star, then your nuclei will grow. If your nuclei is smaller than r star, then your nuclei will become smaller, right? Because above r star there is a net gain in gives free energy as you become bigger. Below r star there is a net increase in gives free energy. So, that is what the general discussion of nucleation is. This is a very well known phenomena. People who are from chemical engineering or materials would probably be familiar with this, and it is very simplistic form. This is what is nucleation. Now, matter cannot be created or destroyed, right. So, where are the smaller nuclei actually going, like why are they shrinking? So, one thing we have already discussed, which is that the smaller nuclei might disappear by adsorption and desorption. The second thing that can happen to the smaller nuclei is they can coalesce into the larger nuclei. So, this is what I am trying to show here. So, supposing you were to form a larger nuclei, then this larger nuclei, because it has larger radius, would continuously suck up more and more of the nuclei that are on the surface and keep becoming larger and larger. In CVD, the small, when we say small nuclei, that small nuclei may be just a few atoms, right. So, yeah, just to clarify. The other things that can happen to these nuclei is that they can do bulk diffusion, right. So, if you, for example, are depositing phosphor, if you have phosphine in your precursor, for some reason that phosphine might start diffusing into silicon, so that can also occur. So, there are several things that can occur to this nuclei. What you want to do in a CVD is for this reaction to happen. You want to actually coalesce into forming a larger nuclei, because that is what is giving you a growth. Rest everything, the desorption, the bulk diffusion and all is subtracting from your growth, right. So, you have to find that temperature pressure window where the rest of these things are not happening, and this process is the dominant one. Let us keep going. Now, one of the things I promised that we will discuss is that we will start with homogeneous nucleation, where we form a sphere. But if you look at this figure, you will notice that with the larger nuclei, I have not drawn it as a sphere, right. So, if it is not a sphere, does the math that I have shown you still hold? It turns out it does hold. Now, that is generally understood in the class of, it is called heterogeneous nucleation. So, this is the nucleation that happens on a surface. So, imagine you have a chamber. What homogeneous nucleation is when this green vapor coalesces into a nuclei that is suspended in the air. So, this is what happens when mist, for example, forms by water vapor in the atmosphere. That is homogeneous nucleation, but when you are doing CVD, that is not the primary mechanism that occurs. The primary mechanism that occurs is that you have a susceptor or a wafer or a surface or a chamber, and on that you start forming a nuclei, and that nuclei may not be spherical in shape. It so turns out that for reasons that will be obvious in the next slide, this heterogeneous nucleation is actually more probable than homogeneous nucleation. And this is very, very important, because if you think about it, if you are doing, say, silicon deposition using silane, and if gas phase reactions start happening more than deposition reactions, then instead of getting a silicon film, you will just have a shower of silicon particles, right. So, silane will break down into silicon atoms, those silicon atoms will form these particles, and those particles will rain down on your wafer, but not give you a film. It does not happen because homogeneous nucleation is less probable, heterogeneous nucleation is more probable. So, you actually start depositing on the wafer before you start nucleating in the vapor. Now, in order to understand heterogeneous nucleation, you need to start understanding how wetting happens. So, this is the idea of contact angle. So, if you remember, supposing you had a substrate and you put a drop of water or any liquid on top, then basic physics will tell you that there are three types of surface tensions that are acting. There is a surface tension component between the substrate and the nucleus. There is a component between substrate and air, and a component between nucleus and air. And under equilibrium, all these three things balance, and they balance at a certain angle which is called theta, contact angle, and at that contact angle these three forces balance, and that is what decides the shape of the nucleus, right. So, for example, supposing you had a material that does not wet surface at all, supposing the surface is, say, hydrophobic, and you put water on top, then the water just sticks like a sphere. So, if it sticks like a sphere, then there is no wetting, right, and the theta in that case is 180 degrees. The other extreme is if the water wets the surface perfectly. If it wets the surface perfectly, then the contact angle is essentially 0. Now, if you look at these formula, which we shall not derive, and I shall not ask you in exams to remember this, you notice that the delta G of this heteronucleation is always less than the delta G of homonucleation. So, just look at this formula. So, it is 2 plus cos theta 1 minus cos theta by 4. So, this whole thing in square brackets is always less than 1 for all theta between 0 and 180 degrees. Let us go one step further. When is delta G hetero equal to delta G homogeneous? It is equal for the case of theta equal to 180 degrees, because for theta equal to 180 degrees you start forming a complete sphere, and that is exactly what happens in the homogeneous nucleation. As you go from theta equal to 180 degrees to smaller angle, the value of this term reduces, which basically means that this value of delta G reduces. Now, if this delta G reduces, then again if you remember this curve of Gibbs free energy versus radius, you would notice that as you reduce this critical delta G critical, you would actually shift the value of R star, right. So, that is what happens. And because this value of delta G is always less, the nucleation on the surface is always more probable, is always more favorable. That is the reason we are able to deposit films and do not have shower of particles. All right, let us move on. Now, once you have the nuclei on the surface, and we discussed that there is this component of wetting, right. So, you can either wet the surface or not. Now, supposing you do not wet the surface, then what often happens is as more and more material comes, it tends to stick to itself and not to the substrate. So, what you can imagine will happen is that you would form these small bubbles on the surface, right, nuclei on the surface, and these nuclei would grow vertically as well as horizontally. So, they would just grow in size because they do not like sticking to the substrate, and if they do not like sticking to the substrate, they will keep growing larger and larger. So, we were becoming larger and larger, and at some point for some large thickness these two would coalesce, and wherever they coalesce you would form a boundary. Often this is a grain boundary or a domain boundary. This sort of process often leads to small grain sizes or small domain sizes. It is called Volmer-Weber growth. It is also called 3D growth. This sort of growth is undesirable for epitaxy because you do not want these boundaries. These boundaries are bad for devices. And the reason for this boundary is because this nuclei that is growing and this nuclei that is growing are not connected with each other. And if they are not connected with each other, they have no way of communicating the orientation or the crystallographic orientation with each other, and hence they each grow in a different orientation, and when they meet at the boundary and because the orientations are different, you tend to form a grain, right. The other disadvantage of this sort of growth process is that 100% coverage is only achieved for thickish film. For thinnish film you tend to form these islands that are sort of disconnected from each other. This is, however, a very common case during heteroepitaxy. So, if you are trying to deposit gallium arsenide on silicon, this is the general thing that would occur. However, when you are trying to do silicon on silicon, the problem of wetting is not that severe and you form good films. So, that is a good place to stop. In the next lecture, we shall start looking at 2D growth, which is the case that you actually want in heteroepitaxy. We will look at nucleation, the rate of nucleation, the density of nuclei, which decides your grain sizes, and certain other aspects of what allows us to do epitaxy. Thank you.